Hi, welcome back to my channel, Physics Form 4 KSSM. So today I want to discuss Chapter 1 Measurements on Topic 1.1 Physical Quantities Part 1. In this video, I will discuss 4 learning standards. The first one, explain physical quantity. The second one, explain with examples, base quantities and derived quantities. The third one, describe derived quantities in terms of base quantities and their corresponding SI units. And the last one, explain with examples, scalar quantities and vector quantities. Explain physical quantities. This one you have studied earlier in Form 1, so I hope you still remember what is meant by physical quantity. Physical quantity is a quantity that can be measured, meaning there must be measuring instrument that used to measure its magnitude. Physical quantity always stated with magnitude and unit. Look at this example. Length, the symbol used is L, equals to 150 centimeter. The magnitude is 150, means the value. And the unit is centimeter. The speed v equals to 25 meters second to the power -1. The magnitude is 25. The unit is meter second to the power -1. So physical quantity is always written with magnitude and unit. Now we look at physical quantity units. The metric units is the unit that we always use in physics. When we measure physical quantities, the unit stated for the physical quantity normally is metric unit. Example of metric unit is centimeter, kilometer, kilogram, meter cube, Pascal, and many more. Another unit that also can be used but seldomly used, jarang sekali digunakan, is imperial unit. As example, inch, gallons, feet, pounds, PSI or pound square inch. Okay, so this one is imperial unit. If you look at the old unit used, this one is the unit that used, inch, feet, pounds. Okay. Example in measuring instrument that we have, like ruler, there's a scale using metric unit in centimeter, and there's also a scale for unit, imperial unit, that use the unit inch. Okay, another example, pressure gauge. In metric unit, normally we can use Pascal or kilopascal, but sometimes it's also stated in PSI or pounds per square inch. Okay, so this one we call it imperial unit, but nowadays is very seldomly used. Okay, so physical quantities can be stated in this metric unit or imperial units, but in study of physics in the SPM level, normally we use is metric unit. Next, explain with example base quantities and derived quantities. So for this part, I want all of you to recall what you have studied in Form 1 about base quantities. Did you remember what is base quantities? We can list out base quantities. There are 7 base quantities here. Mass, symbol M, and the unit is kilogram. Time, symbol small t, and the unit is second. Length, symbol is L, the unit is M. Temperature, symbol capital T, the unit is Kelvin, capital K. Electric current, symbol is I, and the unit is A or ampere. Luminous intensity, symbol is IV, or the unit is CD or candela. And then the last one, quantity of metal, we use the symbol N, the unit is mole. Next, for derived quantities, These are some examples of derived quantities: area, density, force, pressure, voltage, momentum, and acceleration. Look at this table: derived quantity and its symbol, and also formula. For example, volume. The symbol is V. If you, I think all of you know about the formula for volume. Normally we just state as length times width times height. Okay, so actually the width and height is under group of length. That's why we can state the formula as length times length times length, or length cube. So the formula for volume, V equals to L to the power 3. For density, rho equals to mass divided by volume. Okay, velocity V equals to displacement divided by time. Displacement is under group of length. So we also can state as V equals to length divided by time. For charge Q is Q equals to current multiplied time. As you can see here, for derived quantity, there's a formula. Why there is a formula? Because actually derived quantity is related to base quantities through a formula. When we use formula, meaning there is an operation of multiplication and division. Now look at the definition. From what we discussed, we can say that base quantity is a physical quantity which cannot be derived from another physical quantities. As an example, time taken. You can measure time straight away by using stopwatch. No need to use formula to calculate again for time taken. Or you want to measure mass of an object, straight away you can use a weighing balance. You can determine the mass of the object. So no need to use a formula. So it's base quantity. How about the derived quantity? So derived quantity is a physical quantity that can be described in terms of base quantities. Meaning, as you can see, base quantity we discussed there are 7 base quantities. Other than that, all are derived quantity. Okay, so derived quantity, there must be formula that shows combination of physical quantities to form derived quantity through multiplication, division, or both of operation. Okay. Let's describe derived quantities in terms of base quantities and their corresponding SI units. Example, we have density here. Formula rho equals to mass divided by volume. Now we want to state the derived quantity in terms of base quantity. For mass, this is already base quantity, so we just write down m here. Volume is equals to length times length times length in terms of base quantity, or m divided by L cube. So you want to derive SI unit for density, we just look at the formula that produced in terms of base quantities here. So from here, unit for m is kilogram, unit for volume is meter cube. Thus, we can write it again as kilogram meter to the power negative 3. Look at this table. Now we want to complete this table. So from the formula given, you must be able to write the derived quantity in terms of base quantity and then derive its unit. Area A, area, formula for area is length times width, for example, but width is under group of length, thus we can write A equals to L squared. In terms of base quantity, is length times length. From this formula, we get SI base unit as unit for length multiply unit for length, that is meter times meter. So we get meter squared. For volume, volume is L to the power 3. So L times L times L. So the unit become meter times meter times meter, or meter cube. For density, rho equals to mass divided by volume. Volume just now we have already derived is L times L times L. So equals to L cube. Thus density in terms of base quantities is M divided by L cube. Now in terms of SI base unit, it becomes unit for mass kilogram divided by unit for volume meter cube. Thus we get kilogram meter to the power -3. For velocity is displacement divided by time taken. So in terms of base quantity is length divided by time. So now you want to write the unit for length meter divided by unit for time second. So meter per second become meter second to the power -1. Acceleration A equals to change in velocity divided by time. Velocity we already produced it here as L divided by T. So we just substitute here. So L divided by T divided by T, or we can write as L divided by T times T equals to 1 divided by T squared. So in the unit of SI unit, so we can write as unit for L meter, unit for T squared second squared, then we can write as meter second to the power -2. For force F, F equals to mass multiply acceleration, or F equals to m times A. In terms of base quantity, for A we already produce here as L divided by T squared. So meaning m multiply L divided by T squared, or we have m times L divided by T squared. If you write in terms of SI base unit, it becomes kilogram times meter divided by second squared. Or we can simplify, become kilogram meter second to the power -2. You look at the left column here. This one is specific unit. Sometimes the SI unit, we can write equivalent unit. For example, kg meter second to the power -2 also can be stated as Newton, or the symbol capital N. So I think for the force, it is easier to write by using this specific unit instead of this SI unit. Okay, this one is a bit longer, the unit. This one is shorter, only one symbol N. Okay, so unit for force, normally we use Newton. Okay, now why not you try this one in 5 minutes? You can pause the video, then you can come back and check the unit. Okay, momentum P equals to m times V. In terms of base quantity, we already discussed earlier, V can be written as L divided by T. Thus, m L divided by T. So the SI base unit become kilogram multiply m divided by second. Or simplify, become kilogram meter second to the power -1. Pressure P. Pressure is defined as force per unit area. Force also we have discussed earlier is equals to m times L divided by t squared. Now you just substitute F, m times L divided by t squared divided by area. Area is L times L. So we can just simplify L here and L here can be cancelled. Thus we get m divided by t squared times L. In terms of base unit, meaning kilogram divided by second squared times meter. Or we can write as kilogram meter to the power negative 1 second to the power negative 2. And this one has equivalent unit, meaning it can be stated as Pascal, PA. Energy or work, W. W equals to force times displacement. Displacement is under group of length. So work done or energy equals to F times L. For force, we have discussed earlier, the unit is, or in terms of base quantities is m times L divided by t squared multiply L. So we get ml squared divided by t squared. In terms of SI base unit, thus the unit become kilogram meter squared divided by second squared. Or we can simplify, become kilogram meter squared second to the power negative 2. Equivalent unit for this unit is joule, capital J. So all type of energy or work done, the unit can be used is joule. Instead of writing a very long unit here, you can just write capital J or joule. Charge Q equals to current multiply time. So for the, in terms of base quantities, I is base quantities, so I times T. In terms of SI base unit, unit for current is ampere, unit for time is second, so we get ampere second. And also can be stated as coulomb or capital C. So if you try this exercise and you can get all the answer correct, meaning you are able to state derived quantity in terms of base quantities and able to derive its unit correctly. So recall what you have studied earlier is about SI unit. What is SI unit? SI unit is international unit system that used in most of the countries. Advantage of using SI unit is to ease the technology transfer and the study of physics in higher level in other countries. So actually just like standardize the unit use. In Malaysia, Standard and Industrial Research Institute of Malaysia, SIRIM, is responsible to prepare the standards of all measurements. So for example, if you buy electrical appliance, you can see the symbol or the label, SIRIM is there. Okay, meaning SIRIM already state a standard for the level of the power rating stated at the electrical appliance. Okay, the last learning standard, explain with example scalar quantity and vector quantity. We look at the definition first. Scalar quantities are physical quantities that have magnitude only, meaning just state its value. Vector quantities are physical quantities that have both magnitude and direction. Look at example. For the scalar quantities, speed of a car is 100 km per hour. Length of the rope is 2.7 meter. So speed and length is in group of scalar quantities. You can see how we write just its magnitude, no direction. Okay, examples for vector quantities. For example, the velocity of a car is 100 km per hour towards north. Force applied is 200 Newton to the right. You can see the red color word here. This one actually represents direction. When we talk about direction, we can use compass as a reference for direction, or direction right, left, upwards, downwards also can be used as direction. So once the physical quantity is stated with magnitude and direction, so the physical quantity is under group of vector quantities. Okay, so the physical quantities itself can be divided to these two groups, scalar quantities and vector quantities. Let's look at more example on this. Scalar quantities. Another example that always can be seen in this physics topic: distance, area, length, work, temperature, time, volume, speed, energy, density. For vector quantities, we have displacement, velocity, force, acceleration, momentum. Why do you think scalar quantity no need direction? Because the magnitude of scalar quantity always the same in any direction, or direction does not affect the value of scalar quantities, but it does affect the value for or the magnitude of vector quantities. Okay, so I will stop here for this part 1. I will continue with part 2. So I hope you will continue to watch this video so that you can understand better. Goodbye.